So we then went to notes, and this was the first page. It's page 12 in your packet, and it's a scenario where you've got a stereo, and a company makes them. They take 9 minutes to get them ready to box, which we'll call packing, and then it takes them that with a standard deviation of 1.5 minutes, and it takes them 6 minutes on average to box them after they're quote-unquote packed with a standard deviation of 1. And so we have 2 questions that are going to go along with that, and here's the first one. What's the probability that of packing 2 consecutive systems that it takes over 20 minutes? Well, this is going to take the best of 2 things that we've done and put them together. We did normal probability, normally distributed distributions as random variables. We did that yesterday. And we had rules for combining them or doing linear transformations on them. And so we're going to mix all of that up. Starting out, the question is, which I just said, what's the probability that we're packing 2 consecutive systems and it takes over 20 minutes? Well, this is not one system that we're changing with a linear transformation. These are 2 separate systems. So I'm just going to start out by calling random variable x. That'll be time required to pack the system. Time required to pack the systems. And we're told that x is approximately normally distributed, and it's got a mean of 9 minutes and a standard deviation of 1.5. All right. Well, we're doing 2 of them. So we need to get a mean and a standard deviation for doing both of them, one after the other. If you have 2 things that are normal as far as random variables go, and you combine them, the resulting combination will also be normal. Just keep that in mind. So we're going to do mu of x plus x, and that's just going to be the sum of the mean of x with itself. So that will be 9 plus 9 minutes will give us 18. All right, now we need the standard deviation of x plus x, and that's just going to be the variance of both. Well, it's the same thing twice, so that's just the square root of sigma squared x plus sigma squared x. In this case, it'll be the square root of 1.5 squared plus 1.5 squared, and that'll give us, let's see, 2.12132. Sorry, I'm not doing too much rounding today for some reason. So we're in minutes for both. Might as well put the units in. And so let's go ahead and define a new random variable y. And y will be the time to pack 2 stereos. As opposed to 1. I think that ends with an ES. Or whatever. Not sure about the E. It's like potato, right? So we'll just do that. Okay, this is y is going to be approximately normally distributed with a mean of 18 and a standard deviation of 2.12132. Okay, let's go ahead and draw this out and just get some idea of what's going on. So this is centered now at 18, this new random variable that we just set up, and we're really interested in the probability that y is going to be greater than 20 minutes. So let's mark that off. We'll just kind of locate it somewhere over here. And I don't think it's too terribly far out in the tail, but it's not super close to the middle either. So we'll probably get a modest probability out of it. So this will be the probability that Z, remember we just have to show it standardized, that would be 20 minus 18 over 2.12132. And I'm just going to not do this the long way. I'm just going to go ahead and get the answer here. This is going to be 0.1729. So a little over 17% of the time, it takes 20 minutes or more to pack 2 stereos. All right? So that's a start. This is actually one of the easy ones, but just to recap, we took separate random variables. In this case, it was x and x again, found the new mean, found the new standard deviation, knew that that came from normal, so it's going to remain normal, and we just did normal calculations on it. All right, so question number 2 might be a little challenging because we get questions like these, so I'm going to stick a little star on it. So it says, what percent of home theater systems take longer to pack, so I'm going to call packing time random variable x, longer to pack than to box, and the boxing will be random variable y. Okay? So what I'm going to do is, since we're talking about one thing taking longer, doesn't that imply a difference? Because if you add these together, that's just going to make a big thing, and you won't be able to really separate out the effect of one relative to the other. So this is going to be subtraction. So we'll just set up a new random variable w, and we'll call that the difference. The difference between packing time and boxing time. Packing time and boxing time. And they're looking at x being hopefully a larger thing. So the difference here, we're just going to figure out a mu of x minus y, which will be the mean of x minus the mean of y. Well, I remember the packing was 9 minutes and the boxing was 6 minutes, so the difference is 3. So then we need a standard deviation for x minus y. And even though it's subtraction, you know that that's still going to be an addition for the variance. So that'll be the square root of 1.5 squared plus 1 squared. Remember, you have to go to standard deviation through variance. And that will give us 1.80278. And these are both minutes. So we can describe the distribution W as being approximately normal with a mean of 3 and a standard deviation of 1.80278. Okay, now this one is where we need to draw this out, because otherwise you may not quite get what to do next. All right, this is going to be centered at 3. All right. Now you got to think about where the action takes place numerically when you take a difference, right? If I use 0, for example, as kind of a critical value, anything above 0 is going to be where the difference will be positive, and the packing time will actually be longer than the boxing time. Anything below that, anything negative, will be where the boxing time is actually greater than the packing time. So we're talking about this part of your curve right here. And that's quite a substantial part of your curve, really, because we're talking, this is where half separates half above to half below. This is way more than that, okay? So we're going to be doing the probability that W is greater than 0, and that's where, again, packing will, that difference, if it's greater than 0, packing will be greater than boxing, all right, taking longer. So that'll be the probability, and our observation is 0. Oh, hang on, forgot this. Let me get this off the screen here. This is the probability that Z, let's forget our little friend Z, is greater than 0 minus 3 over 1.80278. Okay? And again, we'll do it the short way. We've shown the standardizing. We've shown the curve. You should get 0.9519 or thereabouts, depending on how this is rounded. But they do want percent, so let's give them percent. This is about 95% of the time. All right, so there you go. Again, just 0 is where the action takes place. 0 is where the two are equal. Anything to the right is where x is bigger than y. Anything to the left is where y is bigger than x. Okay? So you may need to mull problems like that over. You may have to just kind of take a little bit of time and really think them through. Speaking of which, I'm going to take just a second to switch screens. All right, so really what we did in the previous page was all of the notes for today, but I felt that we ought to just kind of knock out one or two of these problems, at least a part of them, so we can emphasize the difference between, combining two different random variables, two independent random variables, as opposed to taking one random variable and running it through a linear transformation. They're different. There's some major differences. So if we can keep those things distinct, then some of the issues we saw in our quiz will kind of go away. So we're really on page 14. This is your homework. And so if we knock a little bit of it out, that'll be fine. This is not usually how I handle this. I typically will do this on a separate sheet of paper. But I want this in front of you so that you can see it. So I suppose, yes, you'll follow my terrible lead and try to squeeze a bunch of work into tiny little spaces, but hey, if I can do it, anyone can do it, right? So the first problem, we're going to do part of it, and it's that old thing we've been working with the American Veterinary Association. So remember, average cost for medical care for dogs is $100, I guess it's per year, with a standard deviation of 30. Cats are a little more, 120 with a standard deviation of 35. We're assuming that they're independent, so they're two separate, distinct things, and they're normally distributed. Okay, that's important. And you have a dog and a cat, so you have one of each. So what we're going to do is set up a random variable x and just say that that's going to be dog plus cat. All right, now I know that I violated the convention and I'm using letters at the beginning of the alphabet, but oh well. Okay, no worries. So we're going to describe this distribution, so we're going to have to combine the two. So we need, let's start with the mean of D plus C, and that's just adding the two means together. So that'll be 100 plus 120 is 220. All right? So we already know that x is going to be approximately normal because the two distributions that it came from are going to be normal, and it's got a mean of 220. And now all we need is a standard deviation. So the standard deviation of dog plus cat, that's going to be the square root of the two variances added up. So that'll be 30 squared plus 35 squared, which will give you $46.10. And that goes here. Okay? So now that we've put them together, it's just normal calculations to finish any kind of questions that they might ask. So I'm a little restricted here in drawing curves, but trust me, what I posted online has all of the curves. So this question says, what's the chance or the probability the annual cost will be more than $250? So that's the probability that x is greater than 250. So we're going to standardize. So that's the probability that z is greater than 250 minus 220 divided by 46.10. And I'm just going to go old school with this. So that's the probability. I'm going to make it into a z-score. Probability that z is greater than 0.6508. And then we just do a normal CDF. And this is greater than, so it's going to go from the number 0.6508 to infinity, or some big number, 1,000. And that's going to equal 0.2578. That's it. That's the first one. Now I'm going to leave C up to you. Probability your annual cost will be within $50 of the mean. Here's your mean. So we're talking, take that value and subtract 50 is 170, and then add 50. That'll be, what, 270? So 170 to 270, you find that probability. Okay? All right, so the last one we're going to tackle is going to be a linear combination. So we've got a test grade that we're going to curve. So I'm going to let random variable y be the curve. And the regular scores were on a distribution. That's going to be normal. I'm going to say x is approximately normal with a mean of 60 and a standard deviation of 5. That comes from, here and here. And we just need to go ahead and convert. All right. So let's go ahead and just say we need mu of y. I'm sorry. Let's say this will be mu of 1.2 times x plus 5, right? And that's just going to take your old mean and multiply it times 1.2 and then add 5. So the new mean will be 77. And since we're starting normal, this linear transformation is not going to do anything to the shape. It's going to stay normal. So y should be approximately normal with a mean of 77. And the next thing we need to do is get sigma of 1.2 x plus 5. And you know right away that this plus 5 in a linear transformation is just superfluous. It moves things to the right 5, but it does not stretch or compress. All right, so what we need, remember, this value here, right there, is going to be your b. So that's b squared times your original variance and then the square root of that. So that'll be 1.2 squared times the original variance, which is 5 squared. All right, and I stopped right here just for a moment because if you look really closely at this, I am squaring and then I'm taking a square root, which is like digging a hole and then filling it back up. Really, that's kind of pointless. Most kids realize that after a time when you work enough of these problems, that really if you want the standard deviation in a linear transformation like this, it's just going to be 1.2 times 5. That's it. You don't have to square and then undo the squaring. It just seems silly. Now in the other version where you're combining independent random variables, that doesn't even involve squaring, the b value or whatever. There really isn't a b value. So this is going to equal, after all of that, 6. Okay? So there is our new distribution for curve test grades. And then after, they want to know what the probability is of a passing grade for any randomly selected student. So this is the probability that y is greater than or equal to 70. And we need to standardize, so this will be the probability that z is greater than 70 minus 77 over 6. And I'll just plop together a small curve over here. Not a great drawing. Remember that's 77. And 70 is somewhere down here. So you're talking about a major amount of this curve, right? Way more than half. And if you go ahead and do this, the quick way, you will get a fairly high probability, and that's 0.8783. So about 88%, if you pick a student at random, they stand an 88% percent chance of getting a passing grade. That's pretty good. Pretty good. All right, so you've seen the two. That's to try to make things a little separate and distinct in your mind as far as understanding them. I don't have the other page, but page 6 will be, page 6. Problem 6 is going to be a little bit challenging. Just going to warn you up front, that's an old AP problem that even bedeviled a couple of teachers, and I did it again the other day, and I really hadn't remembered. It's been so long since I messed with it, but it just came to me pretty quickly how to do it. So play around with it, look at the key, see what you can do with these, get this program down, all right? Get all of your, combining and transforming down so that it's just second nature. Okay, so there is my advice to you.